Continuing our talk about enzymes, we want to get into something that it's called enzyme inhibitors. These are substances that actually block or stop the enzymes from functioning as they were meant to. And we have two different types. We have competitive inhibitors and then non-competitive or allosteric inhibitors. What this is referring to is every single enzyme, the way that it speeds up that reaction is that the substrate is going to bind to the active site on an enzyme. The active site is shaped perfectly for that substrate. So that substrate is going to fit perfectly into that active site in order to be acted on. Competitive inhibitors, they are shaped similarly. They're shaped enough like the substrate that they actually bind onto the active site and prevent the substrate from binding onto that enzyme. So what we see is because they're binding in that space, we get a decrease in affinity for the substrate, which because it has an inverse relationship with our Km, we get an increase in Km. But overall, there is no change in our total V max. As we continue to increase that substrate concentration, these enzymes, the enzymes that are not directly affected by the competitive inhibitors, it's still eventually going to reach that maximum velocity. Okay? The non-competitive inhibitors, however, the way that these work is they actually bind to a different spot on the enzyme. So here we have competitive inhibition. They bind on the same spot as where the substrate wants to bind. The non-competitive inhibitors bind somewhere else, and they actually change the shape of the enzyme and thus change the shape of the active site. So the substrate can no longer fit where it is supposed to. And that's how the non-competitive inhibitor stops the enzyme from working. So in this one, there actually is no change in the Km because it's not necessarily changing the affinity, it's just changing the shape so that it no longer can bind. As well, this is going to decrease the Vmax because it's changing that enzyme's shape. These are the type of questions that you're going to get on this. You're going to get questions about competitive inhibition and non-competitive inhibition and what their effect is on the Km or the Vmax. So this is another one. This is a super easy, two quick things to just memorize. Competitive inhibition, increased Km because decreased affinity, but no change to the Vmax. The non-competitive inhibitors, also known as allosteric, there's no change to Km, but a decrease in the Vmax. And that's exactly how you're going to get asked those questions on Part 1 boards. So again, overall, the summary, competitive inhibitors, increase the Km, no change in Vmax, and you can add enough substrate to dilute out the inhibitor so you get that no change in Vmax. The non-competitive inhibitors, they bind a site other than the substrate. There's no change in the Km, and you get a decrease in the Vmax. A little note, the allosteric enzymes, these are the type of enzymes, I should say the allosteric enzymes, the ones that are affected allosterically. These are the type of enzymes that are going to be the rate-limiting steps for our metabolic pathways. In the future, we're going to talk about the Krebs cycle. We're going to talk about glycolysis. We're going to talk about some of these pathways that have these enzymes known as rate-limiting steps. And these allosteric inhibitors, I should say, chemicals that can allosterically inhibit, are going to be the ones that are our rate-limiting steps. So that actually concludes our enzyme portion. I'm going to throw in just this last little chunk. This is Gibbs free energy. So Gibbs free energy, notated as delta G. Anytime you see this triangle delta, that just means change. So we're talking about a change in energy that is happening. So this measure is a measure of the amount of energy available to determine if a reaction is going to happen, if it's energetically possible. If the delta G equals 0, that means that the whole area, this area that we're looking at for our energy in this whatever specific area, we call that a system. The energy in this specific system or area is at equilibrium. So there's no change, overall change happening. So there's not really any reactions going to happen either way. If our delta G is a positive number, this means that the reaction is non-spontaneous or it's unfavorable. These types of reactions are our endergonic, also known as endothermic type reactions, meaning that when these reactions occur, they need to be fed energy. So cold, when we feel something that's cold, when we have a cold from a chemical reaction, like think about those ice packs that you snap or that you pop and it gets really, really cold. What's actually happening is a chemical reaction is occurring and it's actually absorbing and pulling in energy around it to create and cause that chemical reaction. And that's why it feels cold, because it's absorbing energy. If our delta G is a negative value, that is what is called a spontaneous or a favorable reaction. Those are our exergonic or exothermic heat type reactions. The real questions that you're going to get about this is it's going to talk about the free energy of the reaction is this. So it's negative 4.7. Is this reaction exergonic, endergonic, or whatever? Because we know the delta G is negative, we know it's an exergonic or spontaneous type reaction. That's most everything that you're going to get asked about Gibbs free energy. And that is going to conclude this chunk. In the next one, we might break vitamins and minerals into a couple of videos just because there is a lot to unpack there. So we will go over that in the next one.